All right, gang, our first lecture is going to be pretty short. Why is that? Well, we're going to cover Chapter 1. And Chapter 1 of a programming text is usually an introduction to programming and computers, like what is a computer? Stuff like that. Now, there are some important concepts in here, so we're not going to blow it off completely, but we may not spend more than one lecture on it. So I downloaded the PowerPoint. I just went to Modules, scrolled down to PowerPoint, got it from there. Recommend you read it as well. Look through the textbook. You're on the hook for reading it, but I'm not going to ask very many questions as far as an exam, and I don't even think I have a quiz over it. Doesn't mean I don't want you to watch the video, right? Watch the video, fill out a video review form. Okay, so hardware terminology. We know what this stuff. These are all input devices. Keyboard, a mouse, a scanner. We know what output devices are. Monitor and printer. Nowadays, we have touch screens, which are both input and output devices. And then your computer has a central processing unit and main memory that it accesses, right? So while it's running, it's using its main memory. And then it needs some kind of secondary storage so that it maintains its memory even after you reboot the device. Because you're quite familiar, you restart your computer, any unsaved work is lost, so you better save it at a hard disk or to a solid state drive or whatever, right? So input, output, I/O devices. We're going to be writing programs that, for the most part, in fact, this may be just about always true, uses a keyboard for input, right? Or we can open a file and use that as input, right? You have a data file on your disk and you want to read in from it. That's a form of input as well. And then you have output. Our output is mostly going to be the screen or saving back out to a file. So what is main memory? Main memory is just a big old chunk of transistors or the like that can record data in the form of binary data, which is all zeros and ones. And different patterns of the zeros and ones represent different numbers, right? And if you have text, that text is also saved as a series of numbers. And we could talk about that, but this isn't a fundamentals of programming class, so I'm not going to talk about it too much. But there's something called ASCII text. And if I go in and I Google up ASCIItable.com, ASCII spelled A-S-C-I-I, this is a common coding scheme, common encoding mechanism, where, like, if you type in an A, what's written out to computer memory and what's saved to disk is a 65. And then if you type out, an F, a 70 is saved into memory, and if you write it out to disk, you'll get a 70. So I could go and look at a file that I've done in the past to see those contents. Notice the difference between, there's a decimal column, which means base 10, and a hexadecimal column, which means base 16. And if you took fundamentals of programming, you probably know the difference, or maybe you run across that in another class. We might spend a little bit of time talking about the difference between decimal and hexadecimal, but not today. So if I go to hexed.it, hexed.it, I can go and load up some kind of file, like a text file or a programming file. I'm going to do that. I'm going to go find a text file on the desktop. I think I've got something saved there, like a Python script. There we go, there's a Python script. Not sure what's in it, but if we go and look, we can see the text over here on the side. And if we loaded it up as a text editor, like this, right? This is what it looks like in a text editor. And this is what it looks like stored in computer memory as a series of numbers. Now it's stored in hexadecimal in this case, so that's why we're seeing numbers and letters, but they're really just numbers, right? And so if I went over here and I changed this P, this 70, to something else, well, what's one more than a P? Elemental PQ, right? So 70, I could add one to it. 71, well, it's now a Q there. I could save it back out to disk and edit it with a text editor of some kind, and I would see that it now said QYTHON code. So memory, this says, contains stored boxes. They're organized in bytes. Each cell of memory is a byte. What is a byte? It's 8 bits long. A byte is enough, it's enough bits to store a number anywhere between 0 and 255. Now that's not really enough to do computing, you know, the kind of computing we want to do where we're doing, you know, cool calculations. Not all of our numbers are going to be less than 255. So we use data types that consist of more than 8 bits or 1 byte. We might use 4-byte data types, which can hold much larger numbers, right? Or 8-byte data types. So whenever Java needs, you know, a 4-byte data type, it asks the, you know, the machine, hey, I need 4 extra bytes to save this number, and the machine gives it to it. So here's their example, right? Memory address 50,000, 50,001, 50,002, 50,003. This is showing that these 2 bytes are dedicated to storing an E, and that these 2 bytes are dedicated to storing an M, and that these 2 bytes are dedicated to storing a U. Now when I was showing you the hex editor, it was 1 letter per byte. But this is showing 2 bytes per letter. Why? It's using something called Unicode rather than ASCII. Unicode allows, you know, letters of, you know, all the different languages, French, German, Russian, you know, Japanese, stuff like that, and not just English. So it's called a multi-byte character set. I'm going to go back to that topic for a minute. Pop open Notepad. You don't have to type these notes in by any means. Don't have to memorize this yet. But if you have 1 byte, that's enough to store a number between 0 and 285. Or we could say 256 different possibilities. If you have 2 bytes, you can store more. The formula for this is n to the power, 2 to the power of n. So if you have 2 to the power of 8, that's 256. If you have 2 to the power of 16, because remember there's 8 bits in a byte, it's a much larger number. 2 to the power of 16, you can have, you know, 65,000 different choices. I'm just going to name that 64K kilobytes. What is a kilo? It's about 1,000. It's a little bit more. But anyways, okay, if you have a 4-byte data type, then that's 2 to the power of, well, what's 4 times 8? 32. 2 to the power 32. Much larger number, right? 4 million different possibilities. Why did I say million? That's 4 billion different possibilities, right? I think I'm going to change this back to being, you know, about 65, right? 0 to 65535 is that range. If you have a 4-byte data type, it can go from about 0 to 4 billion. Or if you need negative numbers, it can go from about -2 billion to +2 billion. This is what the integer data type in this language is. An integer data type is a 4-byte data type. Why don't we change the font size just a little bit more? All right, I suppose I could zoom it. Yeah, that's better, maybe. And then there's another data type called a long. So 8 bytes to hold a single number. So 8 times 8 is 64. So we're going to have to go and Google 2 to the power of 64 to see the values involved. And it's just a huge number, right? It's 18 followed by 18 zeros, right? So, you know, I'm not going to type in all those zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I said I wasn't going to, and here I am doing it. 13, 14, 15, 16, 17, 18, right? It can go about that far, or you could say, you know, from negative that to positive that, whatever, right? It's a huge number, right? So, this is what's known as a long. A long is an 8-byte data type, right? So it occupies, you know, 32 bits of computer memory, 8 bytes of computer memory to store one of these numbers. And you would use a long to hold a great big number. You could use an int to store a number up to about 2 billion, right? But the national debt's larger than 2 billion. The population of the planet's larger than 2 billion. The number of atoms, you know, in a pound of lead is much larger than 2 billion. So it wouldn't be a good choice to store that kind of data in an integer. You would want to store them in a long. So there is two kinds of memory. There's the random access memory, which they're calling main memory. The random access memory is just what the processor can use, you know, has available to it right then and there. If you go and expand your laptop by buying, you know, new memory modules, you're adding main memory to it. Your phone has main memory in it, and that's what gets reset every time you turn off and restart your phone. However, devices also need the auxiliary memory, or the secondary storage. I used that term earlier. Those are your hard drives, or your solid state drives that you put in your laptops, right? You know, does my phone have a hard drive in it? No, but it's got flash memory of some kind that actually serves the same purpose, right? Because otherwise, when you turned your phone off and turned it back on, everything would be lost, and it wouldn't even have an operating system or anything you ever installed on it. So when you look at the specifications for a phone, it tells you the amount of RAM it's got and the amount of secondary storage. So I don't know, let's look up the specs for a Galaxy 10, S10, right? Just picking this at random, I don't know the values. All right, and so an S10e has 6 to 8 gigabytes of RAM, right, main storage, and it's got up to 256 gigabytes of secondary storage. So what's a giga, right? That means billion. Roughly speaking, if you have a kilo, that means 1,000, right? In computer science, it's a little bit different than it is in a physics or chemistry class. In a physics or chemistry class, a kilo, you know, like a kilogram, is exactly 1,000. But in computer science, it's 1,024 because it's based on powers of 2. But they roughly match up, right? And then you have mega, which is about 1 million. You have an 8 megabytes of RAM, that's pretty paltry anymore, right? That would be 8 million bytes. If you had giga, that's 1 billion. And if you have tera, that's 1 trillion, right? And nowadays you buy drives that have terabytes, right? I bought a 2 terabyte drive for my laptop, right? External drive, or to install on my desktop or whatever, right? That's an awful lot of information. Nowadays drives are huge. Vastly more than they used to be. Used to be you'd buy floppy disks that could store only 1.4 million bytes, 1.4 megabytes. Well, you know, you download an MP3 and that's 8 megabytes, so it would take, you know, like 4 floppy disks just to hold that Beyonce song, right? And so that wouldn't have worked. You would not want to listen to a song by loading 4 floppies in a row into your computer. So nowadays, this is the most common, you know, because our memory tends to be measured in gigabytes. And also hard drives go from up into the billions, even up into the trillions, from giga to tera. Did I miss an R in tera? Terabytes? Or is it just a single R? It's a single R. Good. Got it right. Writing algorithms using pseudocode. Now this isn't fundamentals of programming logic, so we're not going to do much using pseudocode. What is pseudocode? It's not a programming language. It's kind of a looser specification for an algorithm that you could then go and write in the computing language of your choice. So I could give you an algorithm written in pseudocode, and you could go and write that in Python or Java or JavaScript or C++ or whatever, right? It's language independent. So what is an algorithm? It's a series of steps that solves a problem. Right? Algorithm, series of steps to solve a problem. Like a recipe to bake a cake is an algorithm, right? It's a series of steps. Seems silly, but it's an algorithm, right? Or you can have an algorithm to calculate the value of pi out to a certain number of decimal points. Sounds weird, but pi is actually a calculated value. Nobody went out and, and measured something. Yeah, sure, the Greeks kind of tried to measure the value of pi, and maybe they got that it was 3 or something, but, nowadays it's calculated out to billions of digits long, just because people can do it. It's an interesting programming problem. There's an algorithm to do it. And then pseudocode, right, is a language-independent way of specifying an algorithm. So it's a specification of an algorithm. Language independent. You're not writing it in C#, you're not writing it in Java or whatever. And a programming language is a language that uses specific keywords and grammar and punctuation in order to express one of these algorithms, to implement an algorithm. So in Java, we use curly braces, whereas in Python, we use tabs. That's an example. In Python, you had to have colons in certain places. In Java, you have to have semicolons in certain places. In Java, everything has to be implemented as a class, whereas in Python, using a class is kind of an advanced concept.
It is.
All right, I'm looking for examples of an algorithm, and I'm not seeing it. Well, what do you know? Okay, so we're going to give it an algorithm anyways. So, like getting pay. And I'm not sure that this is exactly the pseudocode that they're going to show in Chapter 2. But if we want to calculate somebody's pay, we would need their hours that they worked and then their hourly wage, right? So input hours, right? And then input hourly wage, right? And then total equals hours times hourly wage. And sometimes people use the word set there, right? And sometimes they use these funky arrows to indicate that this calculation is being done and stored here. Equal sign's good enough, right? But what if we're implementing overtime? You work more than 40 hours, you get something special. You get time and a half. So I'm going to put an if statement into my algorithm. If hours is greater than 40, then I'm going to calculate a bonus. I'm going to tab it over because all of this only happens if the if statement is true. Right, so bonus is equal to, and this is one expression for it, and I've had people argue about how you calculate time and a half. Trust me, I know that this works, and trust me, I know that you know a different way. Just go with it, right? So a bonus is equal to the hours minus 40 times the wage, so any hours over 40 gets multiplied by the hourly wage, and then divided by 2, because time and a half. How about times 0.5, right? Divide by 2 would have done the same thing. And then we could add that to our total, right? Total equals total plus, bonus. And since we're doing pseudocode, maybe I'll set the words, set in front of everything. And now this is the end of that if block, so I'm just going to put end if. This is pseudocode. It's not a programming language. I can't copy this into Java and compile it and have it run. And then I might output, the total. That pseudocode is it's an algorithm for calculating hourly wage. It's not a program. It's not telling the user what they need to type in or waiting to get input from the user or whatever. There's no print statements, any form of specificity at all. It's just an algorithm. So this is a sample pseudocode. Sample pseudocode algorithm for calculating weekly pay using time and a half overtime calculation. And we could write that as a Java program. Maybe we'll do it next lecture. Let's just get through Chapter 1 for now. Notice I am giving more information than Chapter 1 actually gives, and I will brush against this information again. I'm not just going to make you memorize. For right now, never mention it again, that an integer is made out of 4 bytes and can hold up to a 2 billion number, right? And that you would use a long for anything greater than that, right? I'll mention that again. So the way Java works The way other programs work is, or not all of the programming languages, but for example, C++ is the most common programming language that uses this mechanism, is you write some source code, right? A equals 10 plus 20, print A. Then you run it through what's known as a compiler. And a compiler turns it into an executable. It reads in all the syntax and it writes it out as an executable, writes it out to disk so that it could be run on your program, on your computer. It's kind of a two-step process. Now actually it's more complicated, of course, because everything's always more complicated, but that's what a compiler does, is it turns source code into some kind of object code. What does object code mean? Well, it means something that can be run as machine language. And then the object code gets saved to disk as an executable so that the computer can run it. This means that you don't get the source code for a C++ program usually. Usually you just get the executable. Microsoft doesn't give you the source code for Excel, right? They just give you the exe. Or if you know you're going to download a game on your iPhone or whatever, you don't get the source code for it, you just get the app. That means that it was compiled into an application. There is compilation involved in Java as well, but it's a little bit more complicated. I'll go ahead and take some notes. A compiled language like C++ works like this. Source code is compiled to make object code, machine language, which is saved to disk, and then the computer can run that object code. That's how a compiled language works. Java's a little bit different. So is Python. So are a lot of different languages, but that's how C++ works. Java works like this. It's both compiled and interpreted, meaning that you have source code and it's compiled to an intermediate form. And then when you want to run that, something called the virtual machine, the Java virtual machine, turns that intermediate code into machine language on the spot so that the computer can execute it. So it's a three-step process, right? The source code. Step one is compiled in an intermediate form, and then the Java virtual machine turns that into intermediate code. Well, it's compiled to an intermediate form, and then the Java virtual machine takes that intermediate form as input and turns it into machine language. And then three, that machine language is run, right? This is the interpreting step. That intermediate code is turned I have botched that slightly. No, I didn't. No, I didn't. I'm good with this. There we go. Those are our three steps. Meanwhile, for a compiled language, source code is compiled, and then the computer can run that object code. Three-step process. Why do they do it differently? There are advantages to a compiled language like C++. In C++, all the work is done in advance. You run your compilers, you make an executable, and then you email that executable to somebody else, and they can run it, and it's going to run really fast, right? Because all it's doing is running a machine language file that's been saved to disk. This is slower because even though we have that intermediate code, it has to be turned into machine language and then run on the computer. This is a slow process relatively compared to just reading in machine language from the disk. So compiled languages like C++ run faster, right? But interpreted languages like Java run on are essentially platform independent. I think I spelled that right? So this is the advantage of C++. It runs faster, but it's limited to the platform for which it was compiled. If you compile a Windows executable, then it's not going to run on a Mac unless you do something special, right? Or if you run something to run on some kind of Raspberry Pi, it's not going to run on your Windows program computer unless you do something special, because it makes machine language, and that machine language is tailored very specifically to the architecture upon which it's supposed to write. Right, so compiled languages like C++ run faster, but are platform dependent. Platform dependent. You write a program for Windows, it's going to run on Windows. Interpreted languages like Java are platform independent. I can write a Java program and the same program is going to run on Windows or on Mac or on Linux or my Raspberry Pi. Anything that has Java installed on it can run on my microwave oven, whatever. But it's slower. So there's trade-offs involved. So why are we learning Java? Well, it's commonly used, used in all sorts of businesses, and it runs on a variety of platforms. So it's very useful for companies because they can write some software that'll run on a whole bunch of different platforms, different machines. Whereas you wrote a C++ program, you're kind of limited to its audience, right? It's going to run specifically for the platform for which it was designed. So non-Java programs, the source code, the compiler runs, turns it into an executable. If I could edit this, I'd change it to executable. So what is object code? It's just all the zeros and ones that control the chip in order to make the computer do something. Because ultimately everything on the computer is all zeros and ones. And another name for object code is machine language, right? It's the native language of the machine. And just about nobody actually programs in machine language. Everybody writes in a higher level language, like that, and then lets the computer turn it into machine language. But you conceivably could. So programmers commonly refer to object code as machine code. It's called machine code because it's written in a binary language, the binary numbers that a computer machine understands. So portability is if that same program can be used on many different types of computers. Now I call it platform independent. I'm going to put portable here. So interpreted languages like Java are platform independent. They are portable. They can run on a wide variety of machines. That's why Java was invented. Java was invented not to run on computers, but to run on appliances. Used to be, probably still is, that your microwave had some kind of hardware in it, and your cable box had another kind, and your VCR had another kind. And Sun Microsystems thought it'd be really cool if they could write a language that would run on all those different kind of chips. But then it got used in computers instead and became wildly popular there. And I don't know if anybody's using it for set-top boxes and cable boxes and VCRs and stuff like that. So compiled languages like C++ run faster, but are non-portable. They are platform dependent. If you want to write a Windows program, even if you have the source code for the Windows program and you wrote it in C++, it's not going to work on the Mac because the Mac needs different system calls in order to draw windows and menus and things like that. So it is platform dependent. I think I put the parentheses around this one rather than the other. All right. So object code is not very portable. That's the zeros and ones that actually run it because different chips require different object code. So Java solution to improve portability doesn't compile all the way down to object code. Instead, it compiles down to byte code, right? So the intermediate form is called byte code. It's the first thing that happens when a Java compiler runs. Well, that's what the Java compiler does, is it turns it into byte code and then saved to disk. And then the Java virtual machine, the JVM, turns that intermediate bytecode into machine language when it needs to run. and it does this every time it needs to run. So like object code, bytecode uses a format that works closely with computer hardware, but it's generic. And you can write a Java virtual machine that'll run on a wide variety of platforms, right? You could write one that runs on a Mac, one that runs on a PC, one that runs on Raspberry Pi, one that runs on your watch, right? The same bytecode will work on all of those, as opposed to that executable right up here that's generated. That won't run on all those different platforms. So the same language runs on many different platforms because the Java virtual machine has been written for each one. Now the code for the Java virtual machine is different, right? Because like I said, if you're going to write a program that runs on the Mac, you know, got to be a little bit different than the one that runs on the PC, just different system calls or whatever. But the bytecode is the same. So the source code is the same. Makes it easier on the programmer. They write some source code, it gets compiled to bytecode, and they could either ship out that source code or they could ship out that bytecode, and anything that has a JVM, a Java virtual machine, can run it. So what is JVM? How can a bytecode be run on any type of computer? So as the Java's program bytecode runs, the bytecode is translated into machine language by the computer's bytecode interpreter. It's interpreting it on the fly. Each and every time you run your Java program, this has to be interpreted from bytecode into machine language. The bytecode interpreter is known as the Java virtual machine. So the Java source code turned into bytecode. You can give a customer the source code, or you can give them the bytecode if they're not supposed to be able to modify the source code. Then when they want to run it, they run it on a Java equipped computer that has a Java virtual machine. So that JVM, maybe you've done some, game playing where you downloaded a Nintendo emulator or something like that, right? You wanted to play Super Mario Brothers, Nintendo version, 8-bit Nintendo version. So you downloaded an emulator, and it turns all those bytes that were saved, that were copied from a Nintendo cartridge, and it translates that into the system calls that'll work on your machine. So that's how an emulator works, right? And you can get emulators that'll run, Sega Genesis programs or PlayStation programs or whatever. They all, behave differently because they're all taking different binary files, files that are, so-called ROM dumps of the zeros and ones that are stored in the cartridges. And it takes that raw data and turns it into machine language code at runtime in order to play the game on your computer. And so that emulator is different from platform to platform. You can buy, one for the Mac, or you don't buy, you download one for the Mac, you download one for Windows, you can install one on your Android phone so that you can play Pac-Man on each one of those things. The history of Java. Sun Microsystems thought that putting intelligence into home appliances was going to be the next hot technology, and yeah, it eventually, became true. People nowadays buy programmable light bulbs, programmable doorbells and stuff like that. But, coffee pots and lights that can be controlled by computer programs, televisions that can be controlled in an interactive television, by programs. And so they anticipated a strong market for such things. So Sun Microsystems made a research project. They called it Green. Now I thought that I read that it was called Oak. Called Green. I better delete that question from my exam. Whose goal was to, the code was called Green. The language was called Oak. Anyways, whose goal was to develop software for intelligent home appliances. And so an intelligent home appliance comes from its embedded processor chips and the software. But appliance processor chips, always changing. Somebody comes up with a cheaper chip, right? Or a faster chip or whatever. Engineers are constantly making, processor chips smaller, less expensive, and more powerful. And so the language that ran on the, the older version might not run on the newer one. And so to handle the frequent turnover of new chips, the appliance software must be extremely portable. We've defined portable a couple times. So originally, Sun planned to use C++, but they realized that C++ was less than ideal. It wasn't portable enough. It relied too heavily on hard to maintain things called pointers. Well, we don't care what pointers are. If you've taken C++, you know. So rather than write C++ software, they decided to develop a whole new programming language to handle its home appliance software needs. And their new language was called Oak originally, for the tree that was outside project leader's James Gosling's window. They soon changed the name of it to Java. And then when the home appliance software work dried up, it didn't really become a big thing to use Java in people's microwaves and televisions and stuff like that. Java almost died before being released. However, though it was about the time that the World Wide Web was exploding in popularity, and Sun realized that it could be modified to run, on computers in forms that were downloaded from the World Wide Web to make interactive programs. Because at the time, web programs, websites were not very interactive. You may not have used stuff during the mid-90s, but if you did, the stuff was very primitive. And if you could get a Java program that was very interactive and did a lot of stuff, then it was very useful. So the World Wide Web exploded in popularity, and so did Java. So web pages have to be very portable so that they can be downloaded on any type of computer. HTML is the standard language for web page. But Java programs are very portable as well, and they're better than HTML in terms of providing user interaction capabilities. I don't know if that's true anymore, right? Web pages are awfully complex anymore, using what's known as HTML5 and CSS and JavaScript. What's the connection between JavaScript and Java? You hear both those terms. There's absolutely no connection. The inventors of JavaScript thought, wow, Java's a popular language. If we call ours JavaScript, people will think that it's awesome. So only the names are similar. So Java programs that are embedded in web pages are called applets, except they're not anymore. Web browsers don't support applets. However, you can still download a Java program and run it. Although applets still play a significant role in Java's current success, no, they don't. So this book is several years old. It's probably written during the early 2010s, like 2012, 2013. Some other types of Java programs have surpassed applets in terms of popularity. Java functions chiefly now as either a back-end language that is being run by the server to generate web pages, or as a front-end program to write applications, database programs and stuff like that. So in this course, we cover the SE Standard Edition to write Java applications for the front end. Java programs that run on a standard computer and don't even need the internet. And are there security flaws in Java? Does that make my browsing more vulnerable? No, not really, and that's why Java applets were gotten rid of, so that the internet and your Java programs would not interact with each other, right? There's a hard wall between them anymore. So don't worry that I downloaded Java, my computer is more at risk for viruses. Nah, it's not, because these programs run without even having a web page open, and they don't connect to the internet in any way, unless you wanted to, right? You could write a program that reads from the internet. Maybe we'll do that. You certainly will in advanced Java. And then Oracle bought Sun Microsystems. Oracle now oversees the development of the Java language. Now Java is also used on Android phones, but it's called something different. Oracle would not license Java to Android for whatever purposes. No, that's not the right way of saying it. Google did not want to pay Oracle to put Java on the phones. So they cloned the language. They called it Jarvik, I think, or Darvik. And so they copied the syntax of the language, and there was a big lawsuit, and it turned out that the syntax of a programming language is not copyrighted. So Android phones run something that looks a lot like Java, but it's got a different name. Learning this helps you learn programming for Android. And as a matter of fact, you can actually write Java programs that'll run on Android. They just run through some kind of conversion process before you upload it to your phone. Computer ethics. Yeah, skip that. Chapter 1, quizzes. What is pseudocode? Does it use precise computer syntax? No, it's kind of loosey-goosey. You know, kind of look like a programming language, but I could have written it in some different format, right? Up here, instead of, what was it, input hours, I could have written get hours from user, right? It still would have been just as understandable. I made it a little bit more generic, and so I said input hours, right? I could say input hours from user. I could put a, output, how many hours did you work? And then I could say input hours, so they've typed it in, and then I could say output, what is your hourly wage? And then they could input their hourly wage, right? But I didn't have to do that because I wasn't writing a program. And then output total, right? Output you earned, right? Plus total. Tell them what they did, right? Now this is a lot more specific. I didn't need to do that for the algorithm, right? I kind of specified more about how I wanted my program to work, but as far as an algorithm goes, I didn't need all that. So pseudocode does not follow a specific syntax. So pseudocode does not compile because it's not a programming language, but it's used when writing an algorithm. So that's the answer to that question. Java programs can be embedded in web pages. No, they can't. And such programs are called applets, but applets aren't used anymore. If you submit your okay, these quiz questions seem to apply to some specific professor, and I don't know why when I downloaded these files from the textbook company, they had specific questions from a specific professor. I just need to delete that. And I need to delete this as well. What happens if you're caught working together on a homework project? You receive a 0 on your homework? Well, that's true. And you're also reported for academic dishonesty. So, don't do it. But anyways, we could delete that page entirely. I probably ought to upload it. Alright, so it was a short quiz, but that's because there wasn't much specific to our language that we needed to cover. Now, if I was going to write a quiz for it, I would ask questions about what is bytecode and what is the Java virtual machine. So read the book, know what it is, right? Because when you get a job, you're going to want to be able to speak intelligently about this stuff. But I'm not going to post a quiz over chapter 1. And I'm not going to ask any homework either. So, you have a break for this lecture. I'll post another lecture on Thursday. There's actually going to be, homework associated with that one. Hope this made sense. Go ahead and fill out a lecture review form and upload it to the folder. Thanks. And which lecture was this? I believe this was lecture B. Not sure about that. Let's go look. Course modules. This may be lecture A. No, I see a lecture A. Yeah, okay, so this is lecture B. Just upload your Java review form into the lecture B folder.